Now we will learn how to find the shape of a molecule from the Lewis structure and the electron geometry. This video should not be watched until you have mastered finding Lewis structures and electron geometries. It will assume that you already know how to do those. So here are some examples of what we're going to do. Let's take the case of carbon dioxide. Let's say you found the Lewis structure. You've identified the pairs around the central atom. You say there's 2 places where there are electrons. 2 gives us an electron geometry of linear. So we know that this molecule will have electrons oriented 180 degrees across from one another. We have a physical model kit that we can look at that will show us what this would look like. Here is, imagine that this yellow is the carbon, and each of the gray lobes attached to it are supposed to be electron clouds. Notice that we haven't attached any oxygens yet. That's going to be important in a little bit. So that is how you can visualize that. Now the shape of the electron cloud is what we learned in the last video, and you get that simply by counting how many places there are electrons around the center atom, and that's all there is to that. Molecular geometry, or the shape of the molecule, is a little bit more complicated. What we're going to do now is we're going to attach an atom where appropriate around those electron pairs, and we see from our Lewis structure that we have an atom, an oxygen, attached to the right, and we have an atom, oxygen, attached to the left. And so now that is the full molecule. The molecule is where are the atoms. And the atoms, you'll notice, are still arranged in a line. So the shape of CO2 molecule is still linear, like that. So the molecular geometry, which I'll abbreviate Mg, is linear. In this case, the two match. The electron geometry and the molecular geometry match, but that is not always true. Sometimes they will, sometimes they won't. Let's look at the next example. Next example is SO3. You can see SO3 has the Lewis structure drawn like that. It does exhibit resonance, although we won't get into that right now. And so now we look around the center atom and we find 1, 2, 3 places where there are electrons, 3 electron domains. So we wish to model that and see what it's going to look like. So we get out some more of these gray lobes and we start pushing them together, and that is, of course, Trigonal Planar. It's a flat, triangular shaped group of electron pairs. You have a pair here, here, and here, 120 degree bond angles between them, and that is Trigonal Planar. Electron geometry, again, notice we have not put any atoms on, so we're going to start sticking atoms on again. This time we're going to remember each gray thing represents a place where there's electrons. So it doesn't matter if it's a single or a double or a lone pair, we're just going to represent it with that gray. This is an electron pair. It's not an atom, just an electron pair. So let's go ahead and stick those on, and I think that you'll easily see that once again the molecular geometry is the same as the electron geometry. The atoms are arranged at each pair the same way. So SO3 would have an electron geometry of trigonal planar because of the 3. We knew that once we did the Lewis structure. And it would have a molecular geometry the same, still trigonal planar. And maybe this is starting to seem stupid and easy, so let's do one where they're not the same, and hopefully that will make it clearer why we're doing this. SO2. If we do SO2, this is the Lewis structure. If we count pairs, there's 1, 2, 3 pairs around the central atom. And that's once again going to give us a trigonal
Would the following students please come to the
planar
office?
structure.
Winters, Matt Akers, Keisha Heddick,
It's always helpful when we do this. So there is our electron geometry. Our electron geometry is trigonal planar, just like before. And so we're going to now take our electron geometry structure, our skeleton, and we're going to stick atoms on. Now this time you'll notice though, there are 3 places where there are electrons, however only 2 of them are attached to actual atoms. There's not an atom here, that's a lone pair. Here there's an atom, here there's an atom, there's a lone pair. So I'm going to stick atoms on, just 2, not 3. So now the molecule itself, where the atoms are here, here, and here. There's not an atom up here, so we can ignore this part now. We can actually take that off. That is no longer trigonal planar. That is not a molecule with trigonal planar geometry. That is a molecule that is just a bent line, isn't it? It's just a bent line. So in this case, we have an electron geometry that's trigonal planar, because that's where all of the electrons are. But we have a molecular geometry that is bent line. And that would be that example. The next one would be CH4. And if we look at its Lewis structure, there are 1, 2, 3, 4 places around it. 4 gives us an electron geometry of tetrahedral. So we're going to start out with something, an electron geometry like this one. We got 1, 2, 3, 4. We have a tetrahedron here. There's our tetrahedron. It's got 4 pairs, 109.5 degree bond angles. And if we look here at our drawing, they're going to attach an H to each part, and so we begin to see a pattern here. Whenever there's one atom attached to each electron pair, then you're not going to see a discrepancy. If you look back on this last example, what made it weird, what made the 2 different, was this lone pair. Lone pairs cause the molecular and electron geometry to be different from one another. But here there are no lone pairs. We count each part. All of the atoms are attached there to electron pairs, and so the molecule is tetrahedral. Molecular geometry is also tetrahedral. A couple other examples. NH3, if we look at NH3, we've got 1, 2, 3, 4 pairs around the center atom. That lone pair there tells you that the electron geometry and the molecular geometry are probably not going to be the same this time. So this time we're going to start out with, again, 4 pairs around the center atom, because that's what we have, 1, 2, 3, 4, electron geometry of tetrahedral. But this time we're going to slap not 4 hydrogens onto it, but 3. So we put 1 here, 1 here, 1 here, and then we're going to leave this one off. We're not going to put that on there because there's only 3 hydrogen atoms. In fact, I'm going to remove this lone pair. And so now we don't have a tetrahedron. A tetrahedron would have something coming up off of the top of it here, but this one doesn't. So it's not trigonal planar either. Trigonal planars are flat. This isn't flat. So the name of this, this would have an electron geometry of tetrahedral, but it has that one lone pair up there, and so that's going to distort the molecular geometry, and this molecular geometry is, there's a name for this, is trigonal pyramid. Trigonal pyramid. So that is that. There's one other example. In fact, this video is exhausting every possibility. There are only 6 possible molecular geometries that you would get on any of your quizzes or tests. There are these 6. And the last one involves water. If we look at water, water has 1, 2, 3, 4 places, 4 electron domains. which means that you got a tetrahedron, just like the last two examples. You have an electron geometry of tetrahedral, so we start out with 4 pairs around the center atom arranged in a tetrahedral fashion. But this time we're going to not put 3 or 4, but just 2 hydrogens on, which means that we're going to ignore these 2 things and ask, well, what shape is left when we ignore those? And now we're back to a bent line. It's a different angle than the last one, but we won't worry too much about that. We'll just go ahead and call them both bent lines. This is slightly different than the other bent line because this is a 109.5 degree bent line. The other one was 120 degree bent line, but we won't split hairs. We'll just call those both bent lines. That's the molecular geometry of water. And so those are the various types of molecular geometries that you can get.